Okay, spectroscopy part 2. Turns out I wasn't blocking this whole image with my body, so that's good. Okay, so we can see where certain wavelengths are absorbed by these elements. They're a gas at the surface of the sun. They're absorbing photons that are coming out. So now Earth doesn't get those photons, and then eventually, well, you get those when the electrons go back down to their lower energy states. Those photons are released, but because the gas is moving, it can go anywhere. So we don't get it to Earth. So we have all those black lines. We're missing big chunks. Let's show another picture. Yeah, so this one. Okay, so you see here's the spectra of the sun, and there's all kinds of black lines where elements and compounds have absorbed those wavelengths. So we don't get them from the sun down here at Earth. Okay, we went over the basic structure of the atom, why that happens, but let's just emphasize. So here's a really good illustration. Here's a really good illustration. So you have the nucleus, there's a proton, you have an electron at the n equals 1 state, that's the base state. So here it gets a photon, right? Now this is a long wavelength, so this photon would only move this electron, there's only enough energy to move it to the number 2. Well, what if it had a shorter? Notice how, here's one wavelength, notice this wavelength is shorter. Remember, shorter wavelengths have more energy. Here there's enough energy for the electron to go. There's enough energy for the electron to go from 1 all the way to the number 3 position. Now this photon is even a shorter wavelength. So maybe this one is blue, maybe this one was in the red region. It has enough energy to take this electron all the way to the number 4, right? So it has to be the right. There's no such thing as in-between states. The electron doesn't stay in between. It's quantum. That's the basis of quantum physics. What'd you do at school today? Quantum physics. Yeah, and you did, right? So that's what happens, right? So photons, now it has to be just right. There could be other photons here. The electron doesn't care. Ignores. When it gets the right ones, it goes up to higher levels, right? So here's how it works, right? So let me check the camera. It behooves me to check the camera for our own good. All right. So here you have a hydrogen atom, right? There's one proton, there's a nucleus, there's one electron. Here comes a photon. It's like, I don't care. It's like Goldilocks and the Three Bears, right? Goldilocks, the porridge was too hot, the porridge was too cold. Only when the porridge was just right did you eat the porridge, right? So electrons are that way. They're like, no, I don't care. You're the wrong wavelength. I don't care about you. But when a right one comes by, it's like, yeah, I like this one, I'll absorb it, right? Different substances absorb different wavelengths. So now this will move up to some higher level, right? But this atom's moving around, the sun is turbulent, right? Sometime later, this electron will move back down to its base state, and now it fires off that energy, but it goes in a different direction. So Earth, so Earth doesn't get the benefit of that, right? Okay. Now, what can also happen, you can have a situation where you'll have a hot gas. You'll have a gas that's heated up on its own. In that case, what will happen is that you'll get an emission spectra where, say, hydrogen lines, you'll have the lines, but they're in the exact same location that for the sun it was an absorption spectrum. For the sun, the surface of the sun is relatively cool compared to the center. So that cooler gas is absorbing the energy that's coming. Now, if you have, say, a neon sign, right? These signs that say, that the store is open or something like that, right? Now, what you have is a gas, but it's not a compressed gas. It's a much looser gas. If you heat that, it will emit spectral lines, but they're in the same positions that the absorption lines will be. In the sun, that gas is compressed because there's a lot of gravity, right? So, but we're not going to worry about this one too much. If you have a hot nebula, nebulas are clouds of gas in space. If they're hot, heated by stars, this can happen. But for the sun, we're not going to worry about those. So, okay. And then here it's just showing different substances where the different lines are, right? This is the sun. Right, we're used to a continuous spectrum. That's what we get when we put light through a prism, right? And the one we're going to be concerned with is the absorption spectrum, where the gases absorb wavelengths that hit them, and then they re-emit them later. This is the one we're concerned with down here, an absorption spectrum. Okay, so every element isotope, remember that just means that there's different neutrons in the element. We're not worried about that. So every element, displays a unique arrangement of lines. The emission, so the absorption lines for the same element are in identical positions. It's like a barcode, right? Let me go back. It's like a barcode, right? When you go shopping, okay. When you go shopping, they don't have the prices on anymore like when I was a kid. They just have these barcodes. Well, they scan it, right? Well, the elements have all these different spectral lines. So when you take the star's light, distant star's light, right? It's through a telescope. You run it into a device called a spectrometer. It analyzes the positions of those lines, and you can tell what elements are in these stars even though they're so far away. They've run experiments on Earth where they've taken all the elements, all of them. They've analyzed their spectra. They've done it for all compounds, right? Compounds are when elements form, right? Like water is a compound. You have hydrogen, H2O, hydrogen and oxygen. So that's a compound, right? So they've done it for all these substances. They know what the spectra are. Well, you see the spectra coming from different stars. They match it up to what we know on Earth, and you know what's in those stars, and you know it, right? It's like a barcode, all those lines. So they feed it into computers. There's huge databases. In the same way, it's like, boop, oranges, boop, toothpaste, right? You're scanning these things. You're like, oh, we have hydrogen in that star, or we have helium in that star. Like that. It works like that, okay? You can also tell the temperature of stars because at different temperatures, different reactions occur and that sort of thing. Well, they know from running experiments on Earth when you're going to have a preponderance of certain elements and certain things that are going to happen. So when you see that in stars, you know what the temperature of the surface of the stars is too. Even though they're so far away, we know what the temperatures are, okay? Something else you can tell is the movement of the stars. Are the stars moving away from us? Are they moving towards us? Well, while I'm talking about this, so here, you should have read all this already, right? So here's the book, right? So this was chapter 5. Radiation and spectrum. You should all have read this already, right? So go to Files, right, in Canvas, 148 to 58, read that, right? Read these pages. All of this is in the book. You really have to read the book these days. I mean, you cannot not read the book, right? So Doppler shift, right? Well, we know if you're standing, on a corner and a fire engine comes by, the sound changes, right? I'm not going to mimic it very well, but it goes like, right? So if a siren is just sitting there, you just get a steady tone. If it's coming towards you, you get a higher pitch tone. If it's going away, you get a lower pitch, right? It's kind of like as it goes away, right? That's called the Doppler shift because the waves get compressed. So here you have a person standing here. This fire truck is moving. This person is getting a lower pitch as it goes away. This person is hearing a higher pitch as it approaches. Well, light does a similar thing. If you have a star in space and it's coming, if this is Earth and it's coming towards us, the lines will get compressed. They will get, the spectral lines become shorter. Well, because blue is near the shortest end of the visible spectrum, we say that is becoming blue shifted, they don't necessarily have to turn blue. It's just if they get shorted, we say that's blue shifted. It's just nomenclature. And say if this is Earth and there's a star moving away from Earth, well now it's like those wavelengths get stretched out and they get longer. Well, red is the longest wavelength we can see with our eyes, so we call that red shifted. It's gotten longer. Okay, so how does that work with spectra? Well, look at this. So this is very subtle. This is at rest. So this is if you have a substance, say this is helium, and say it has different lines where the electrons can go to different energy states, right, from absorption. Then at some point they come back down, right, and that's just happening. With our sun is in the same place in the sky, so it just gives us this steady thing. But now say you have a star like our sun, and it's moving towards us. Well, now look at this. This line here is kind of in the red-orange, but it's moved here, it's moved towards the orange. These lines here have moved a little bit this way. This line here, which is green, has moved towards blue-green, right? And then this line here, which is kind of blue-purple, right, has moved towards into the purple. So everything's been shifted. Now if there's a star that's moving away from us, everything is red-shifted. So if you compare it to this line, here it's orange, well, it's shifted into the red. Here it's kind of a yellow-green, it's shifted into the yellow. Everything is shifted that way. We call it red-shifted. So we can tell the movement of stars in space, and we know that we know it. So spectroscopy is powerful. We can tell the substances that are in the stars. We can tell we can tell the temperature of the stars. We can tell the movement of the stars. Now the star has to be moving towards us or away from us in order for this to happen. If it's moving side to side, that doesn't work. But if it's going towards us or away from us, then if it's moving at an angle towards or away, well, we can figure that out using trigonometry, which we're not going to get into here. But that's not hard to do. Okay, so we can tell all those things from spectra. It's amazing, right? So that is the power of spectroscopy, right? Make sure that you read the book. It's totally important that you read the book, right? Go to files. I have all, this is the minimal reading assignments, right? Okay, so have fun, right? Try and invent the calculus and physics just like Newton did when he was hiding out, when there was pandemics back in the old days. Okay, folks, see you later.